Okay, this is the AirTex project, and basically it's an LED wand. Now this is kind of inspired by all the POV, persistence of vision LED projects you see on YouTube. Most of these are like mechanical fan type structures, or some kind of orbiting structure, or a metronome type deal. You've seen metronome clocks. All of these have a fixed point, like a LED or infrared sensor that can mechanically tell when the mechanism is at a certain point, so you can sync the software to the motion of the device, whatever it is. Well, this is going to be based on a freestanding deal you hold in your hand, the LED wand, and the sync device is going to be an accelerometer. Now, I have no idea if I can do this or not, so we're just going to have to see how it goes. So let's just take a quick look at the schematic. It's going to be battery powered, of course. Exactly what this battery is to be determined. We're going to need a regulator for 3.3 volts and a regulator for 5 volts. 5 volts is for the processor. 3.3 volts is for the accelerometer. We're going to be using a PIC18F 2550. You'll see in the video I actually shot the part of the breadboard and the scope shots using the 16F 876, and you might notice the wiring change. The 2550 has the same number of pins, so it's not real obvious, but there are wiring differences. Basically I upgraded just due to physical parts on hand reasons. I do have a problem with the it looks real good on the liquid crystal display, but I do have a problem with the code for the F250, and I just can't, F2550, and I haven't been able to figure out exactly what it is. So if you use the code, you're going to see the problem. I'll talk about that more when I talk about the code. The accelerometer is going to be the ADXL345, and it's actually on a mounted on a breakout board from DFROBOT. It's a SEN0032, and we'll be using that part for this. Here's the serial liquid crystal display. As I say, that's optional, and it's really for debug. And this area right now is kind of a placeholder. It's generally, we're going to hook up 8 LEDs, and they're going to have transistor drive, and exactly what the circuit's going to be, I don't know yet. I think I'm taking a flashlight that I had, going to take it apart and use part of it. And so when I get all that worked out, this schematic's going to be modified. But basically we're going to have transistor drivers driving a bunch of LEDs, at least 3 to 18 LEDs, I'm not sure. So that's basically the schematic. And with those changes, note those differences when you see the rest of the video. So let's go ahead and look at the breadboard. Okay, here's our breadboarded circuit for the ADXL accelerometer. I breadboarded it up just so I could get the basic SPI working between the PIC and the ADXL, and make it a little bit easier to troubleshoot before I go to the actual wand. So here we got the PIC, of course, decoupling and decoupling there, running at 16 megahertz on 5 volts. We've got our LM1117-3.3 that provides 3.3 volts to the ADXL. Got the output 10 microfarad and there's another input 10 microfarad back here. Here's our ADXL accelerometer board. It of course requires 3.3 volts. I've never found a schematic for this guy anywhere, but it's pretty simple. Apparently this little SOT 23 here is a voltage regulator, and what it does is supply voltage to VDD IO pin on the ADXL chip. And in the data sheet they're pretty concerned about noise caused by the IO getting into the rest of the system. So they talk a lot about decoupling, and I think that's the reason why this is here. We're feeding in 3.3 volts, and this regulator appears to be a 3.3 volt regulator. So I think it's just providing some decoupling and isolation is about its only purpose. And that's the only extra components on here, decoupling and this voltage generator. Otherwise, there's no other chips on here, no resistors, pull-ups, anything like that. So anyway, I think this board, it probably saves us a lot of hassle with decoupling using this board and over just the ADXL chip alone. And it gives you a way to plug it into a breadboard too. So okay, we got our 6 lines between the PIC and the accelerometer. Of course 4 for SPI. 2 of them are interrupts from the accelerometer back to the PIC, and power and ground. So what we do for the signals coming from the PIC, they're of course out of spec. They're too high voltage. They're running in the 5 volt domain, and we're coming over here to 3.3 volts. So we need to cut our outputs down from the PIC, and we do that with the resistor network, resistor divider network we saw in the schematic, and those are here, here, and here. So and those values, static value on there when it's high is like 2.7 volts, and which is fine for the ADXL inputs. In fact, the margin is I think the margin running, actually getting 3.3 volts out of this, 3.2 volts out of this regulator. There's got to be a little drop in there from 3.3 volt input from this guy. So the voltage input high for the ADXL then is about 2.56 volts, and the PIC, this divider network, the signals from the PIC, we're putting out 2.7 volts. So we got, it's kind of small margin. It's only about 1/10 of a volt, and but we'll see if that works okay. The problem we're having though is going back the outputs, the SDO from here to SDI on the PIC, and the 2 interrupts being driven from the ADXL back to the PIC. The voltage levels on those are 2.72 volts for high. And then if you read the PIC spec, voltage input high is 4 volts for the int and the 2 ints, and 3.5 volts for SDI. Now those are that's because port C, which is where all these signals are coming from, are Schmidt trigger inputs, and the spec is 4 volts or 3.5 volts. The SDI line's a special case for some reason. I'm having a hard time even believing that's true.
because that's awful high for an input high. The regular TTL input high is much lower. So anyway, this shouldn't work. We shouldn't be able to see our interrupt, and we shouldn't be able to see our data back. But got it hooked up. We'll just see how that goes. Now what this chip's programmed to do is the self-test on the ADXL. And that consists of 4 different tests doing 2G, 4G, 8G, and 16G. And those are sensitivity levels, essentially. So this code runs through the that sequence. It does one reading at each of the G levels and just repeats. And we'll go into what you do with these values and basically zero out your error at idle, and then make use of those offsets. So what we're going to do is fire this guy up and see if the self-test works. And what it does, it's going to set each test, and it takes about 16 seconds before it does the next test. So it makes for a longer video, I guess. So let's go ahead and start this up and see if we're getting any data back. So here it says 2G, so we're doing the 2G test now. And these are huge numbers. I think this it powers up with way out of range numbers. So you see when it goes to 4G, it's going to settle into numbers more like this. The FFFD here is minus what FED, minus 3. And that's the X direction. The Y direction is 1F. It's kind of a large offset. Z, of course, the way the board's sitting is the gravity, so it's going to show some significant number for gravity. Here we're back to 2G, and you can see it was like the other 3 readings. .4G coming up here. Yeah, they're very similar. Negative 3 or 4. Value seems typical. The Y direction seems to be pretty constant. Here's the 8G test. Z is in the same range. And there's 16, and so pretty much all the G tests are pretty similar. What you're supposed to do is like take 10 readings, average them to get your baseline values, and you can zero it out in your software. And then when you read actual G forces, you know what your 0 point is, and you kind of adjust them based on that. So one thing we can do is change some of these numbers is to pound on the board a little bit. So I'm going to pound on the breadboard some, and okay, I'll do it for 16G, see how that goes. You ought to see a jump in something, and it's kind of random when I hit it, so there you can see a change. Most of the change is going to be in the Z, because this is essentially bouncing it up and down vertically. There, got a good change. FA. X is hardly affected. Y is affected a little bit. 4G. Whoa. Well, we got the Y. I think I wiggled the board. See what 8G says here. 9C. So you can see it does have an effect, especially on the Z. Looks like I caught it on the downstroke there. Got a big negative number for Z. So anyway, that's basically what this thing does is reads the G forces applied, and it looks like we're getting we're getting data. So I guess the next thing we'll do is just hook it up and take a quick look at the SPI bus, and it looks like the test is using one of the interrupt lines to tell when the test is ready. So to me it looks like it can see the interrupt line and SDI, because it seems to be getting reasonable values back. So anyway, let's look at the SPI bus and on the scope and see what it looks like. Power up, and let's scoot over to the start here. Let's turn our decoding on. Okay, so the first thing we do is you read the ID register at which is register 0. Now in the format for this we discussed going over the code. The bit 7 is the read-write bit, and read is high for a read, and bit 6 is the single multi-bit, and it's 0 for single and 1 for multi. So this is a read of register 0. The rest of the bits, the remaining 6 bits, are the register address. So that's a read and register bit 0. And that's the ID register, as I said, and we're going to clock out that byte, and we get an easy 5. And you'll notice we got an easy 5 over here when we sent the register command. And I've noticed that this ADXL chip always sends out something reasonable. When it doesn't know what to send out, it sends out an E5, and otherwise, if it has previously sent some data out, it repeats that data if it's not actually a read cycle. So it's always putting something on the SDI return that means something rather. Okay, the next transaction is we write to the rate register, which is 2C. So that's again, the read bit is set and register address is 2C, and we clock out that. You notice we're still getting E5, and we clock that data out and we get 0A, and that's the default, that's the data rate, and that's the default data rate, and we're just checking to see if that is in fact set in the default without us doing anything, and that's what we're going to run the self-test at. So all that's cool. We're going to march over here. Look at our next transaction is to the data format register, and that is register 31. So we see our read-write bit is low, so we're doing a write, and that bit 3 is the full resolution bit. Now we write 2F with 0, 0. That's the interrupt map that maps all the interrupts to interrupt 1, and that's what we're monitoring in our software right now, is just interrupt 1. You notice 0A is coming out all the time. The next write we do is register 2 easy, which is the interrupt enable. You send an 80. That's the that's for when data is available, data ready bit. So that's what's gonna cause the interrupt on interrupt pin 1. Then to register 2D is the power control, and we write a 08 to that, and that bit set high. Bit 3, that's the measure, it enables measurement mode, and that increases power on the chip, so you can turn measurement on and off to save power. And then we write a 31, which is again the data format register, and this time before we wrote an 8 and this time we set the bit 7, which is the test bit, which is a self-test bit, and self-test starts, and then we wait for the interrupt to occur on B, and didn't get that, and so then we're ready to read our data, and we must have gotten I monitored the interrupt on port and another pin on port C, which isn't on the scope, and I got that, or I wouldn't be starting this sequence. And this sequence with F2 reads register 32, which is the X least significant byte, and F, we're doing a read in the multi-set. So bit 7, bit 6 are both set. That's reading multiple bytes, and that reads continuously however many you want to read, starting at this first address. So 32 is the X register low bit, then they're all in a row. 33 is going to be 33, which will be over here, will actually be the high bit. Then it's Y high and low and high, and Z low and high. So what we got was FFFE. You remember that was pretty common for the X bits. Negative, we saw negative 2, 3, or 4 was typical. Crank her on over here. Cranked it too far. Sometimes this guy takes off and zooms away on you. Next is Y, 001F. We always saw it was Y was always 0020 hex, in that range, usually a little bit less. So, and here's the Z data, and 0 F3 F6. So that was typical also. That's going to have a good size value on it because Z's the essentially the gravity. So that's affecting the reading there. And then we shut off the test by going back to data format and writing 0. And that stops the test measurement. We wait about 16 seconds and do the next self-test for the next G level. So turn off decode here, and we'll look back at our level on our SDI pin. And you can see here the bottom trace is the SDI. You can see we're down 4 volts or less, probably less than 4 volts. I think this is cranked up a little bit to be not quite on the 0 baseline. So I think we're a little under 4 volts. So we're reading it, apparently though, we have to be reading it correctly. So that's probably not meeting the spec for the Schmidt trigger inputs, but the scope decodes it all right, and I see it, I read it back all right on the pick. It's a little concerning. I don't know, we might be right on the hairy edge of this signal, but we don't seem to be getting any missed values at all. Everything seems pretty consistent. That's probably something to worry about in the future, I guess. So okay, well, it looks pretty good. Looks like our SPI is working, and we understand this part of it anyway. So let's go on to maybe going on to putting this on the wand and trying to figure out what values we want to get out of it when it's on the wand, and what makes sense and what works.
Okay, we'll just take a quick look at the code. As I mentioned before, I've moved from the 16F876 to the 18F2550, and that's made for quite a few changes. And I do have one problem. I apologize. I'm putting this code out here with this problem. I've tried to find it, but I can't. It just involves the LCD driver. There's a couple of bogus characters, and after the first 2G test, it puts the X data on the same line with the Y data at the beginning of the line. I just cannot find out what it is, but since it's not a critical final part of the design, it's just for the LCDs, just for debug, I just decided to leave it, and you know, that driver's coming out as soon as we go to regular hardware. So I apologize for that, but I just can't find out what it is. Now, this is the first time I've used, well, it's the second time I've used the 2550, but I'm still learning it, so I wrote this all in assembly language. So I've got a lot of the register notation in here, and the configuration, all the configuration data is spelled out. I've got my ASCII art going, all the new registers, so I get to learn those. And there's one thing about it, unique thing about the 18F family is its capability of doing indexed memory accesses, and the use of the FSR registers and indirect addressing has been expanded, and so a lot of that stuff is new. So basically here in the setup, pretty straightforward. To get down to here, I'm using the USART facility, of course, for the LCD driving, and I'm also using the SPI to talk to the accelerometer. Well, there's a conflict there where the serial port will not work with the accelerator. Some configurations of the USART and vice versa. The USART won't work with some configurations of the SPI bus. So what I've discovered basically is that everything works pretty well if you only enable the USART functionality when you want to write to the liquid crystal display, and as soon as you're done, disable the USART, and the SPI bus always works that way. So that's how I resolved that. I've seen some stuff on the microchip forum that suggests doing other things, but this works real well and it's real simple to do. So, and after we get rid of the LCD, it's not going to even be an issue at all. So basically that's the main thing you have to worry about in the configuration. Here I've got all the more ASCII art for the accelerometer, and a bunch of new stuff to figure out. Basically the loop here, this solid isn't in it. The accelerometer test itself just uses the test function of the ADXL345, and basically I set 2G, 4G, 8G, and 16G and run a test, and there's 16 seconds separating each test so you can read the display. And other than that, it just keeps it going in a loop doing the test function. And this basically proves out that the ADXL is talking and we understand how to access it. Here is where we send it the first setup messages. There's read and write, read ADXL and write ADXL registers. This ST drive manages the actual reading of the display. XYZ read reads the data from the ADXL chip, and also calls the routine that converts it to ASCII, and then that ASCII gets displayed on the liquid crystal. And here is the D4A, is the part that actually sends the data to the display, and that's somewhere in here is my problem, and I just can't figure out what's going on. It works the first time. After that, it's messed up, and I just don't see where it is. Here's the binary to ASCII conversion. If you need a binary to ASCII conversion with anything, just pick this out of here and, you know, modify it for a number of characters and things like that. And basically, here's the LCD. You've seen this before. This is this has been used in in other projects that use the liquid crystal display. And their delays, I've got some weird delay. I was experimenting here, so use this or not. And here's the text for the display. So that's that's basically the code. Let you go through it in detail. If you like assembly language, you might be able to pick some stuff up from it. You might be able to fix my problem. So the next time I get back on this project, I don't know, I'll be interleaving projects, you know, back and forth. So this will take care of where we are so far. The next thing I'll do is get it on a board, and I'll probably look for a Bluetooth radio to stick on here in place of the LCD to get data off of the wand, so I know what so I can get an idea what the accelerometer data is giving me, and hopefully that'll help debug the wand. So that'll hold you till next time. Thanks for watching. We'll talk to you later.